will ask me, just use the translation Claire from now on, if you want to. So today, first of all, thanks to the organizer committee who brought me here for this talk. And today I'm going to talk about the symmetries that start from the HB phase. So where do we look at HB stars? We have studied the asymmetries all the way from post-HB in planetary nebulae, and we see complex structures, of course, nothing to do with spherical symmetry anymore. But we do mention that those should start from the HB phase, because the stars evolve more or less from the HB onwards to the next phases. And so far, we believe that one of the main shaping agents is binarity. From in the post-HB and the post-HB and the planetary nebulae phase, we see all these intricate shapes. But can we detect this in HB stars? Can you find binaries with HB stars? And if so, if you can only detect the binaries, can you find symmetries in the HB stars that point to binarity? And some examples with wide binaries though is Myra, W Aquila, Arquiris, P1 Gru, SS11, AFGL3068 have been detected so far. Now, for asymmetries in the HBs, we see that the circumstellar envelopes are not always, the extended circumstellar envelopes are not always round. So I have a couple of examples here, and you've already seen the talks that we had a couple of last days. So the examples here are 3 carbon-rich stars, and from the left to the right we have near-infrared maps on the J, H, and K bands. So we have CIT3, IRC 10216, and CIT6. And I would like you to look at the scales here. So this is about 200 milliarc seconds. This is about 200 milliarc seconds. The star is over here. And this is about 50 milliarc seconds. So just within the star itself, so which is more or less 20 milliarc seconds or even larger at the phase that was observed, you see an asymmetric extended envelope or clumps, or some kind of spiral form. Well, I wouldn't say it's spiral exactly, but. And now to observe those asymmetries. So the pictures I showed you before, they were taken by spectral imaging and aperture masking observations. So this is interferometry with a single telescope. The talk earlier ago by Claudia was interferometry with the VLTI, so this is very small spatial scales, and that's what you want to look at. So you want to see within 0.5 arc seconds. So you use the VLTI for even smaller spatial scales, so less than 30 milliarc seconds, but if you want to look at something intermediate, you can use aperture masking. And the advantage is that you can use a large telescope, you can have a range of wavelengths observed at the same time. It has an excellent UV coverage, and it goes down to resolutions of about 20 milliarc seconds each, and we also have a relatively large field of view for about 400 milliarc seconds. And the down point is that you need really bright targets, in which case HB stars are a really good option. So in aperture masking, basically you have, this is the pupil of the 18-meter telescope on the VLT. You put at the pupil plane, you input a mask like that. This is about 2 centimeters. This is not the exact mask we use, but it's an example. And what you get is an anodized pupil. So each mask now, each hole in the mask will represent a hole on the pupil, and each separation between 2 holes is now your baseline. And your baselines are from 0.5 to 8 meters. And what you get is you get some spectrograms, which then you Fourier transform, and you get your visibilities and your closure phases and lots of Fourier details that don't much bother you about like that. So the good thing about this is that you can make recreate images. And we observed 2 stars. One is a carbon-rich star, Lykou. The important part of this star is that it's in transition to the post-HB, and it has 2 peculiar pulsations. One is about 490 days. This is the pulsation of the star. The other one is 17 years, and it has been attributed to the companion, so we call this an obscuration event. It also has bipolar outflow, so this is a paper by Hirano et al., so this is just an image, not actual data, of course. So you see it has a torus about 8 arc seconds in diameter, a bipolar jet, and They've also found, Ravindra found a couple of years ago that there is a smaller disk inside of about 0.5 arc seconds due to scattering in its alpha. And a couple of years ago, there have been some observations with MIDI, so this is a very small spatial scales, and they needed two components to reproduce their data. So you have one component for a star, a component for a disk around it. And the size of the star, I would like you to remember, this is about 20 milliarc seconds in age. So it's the size of the star plus the extended envelope. Okay, so we did some observations with the VLT. So on the left, you'll see this is an image by Eric Legadek in February 2007. This is by Lykou at 374 micron, and you see an extended envelope with about 3 arc seconds. And the core inside is unresolved, but it's a bit elliptical, let's say. Now, on the same filter, we observe the aperture masking, and now you see that the resolution is much better. We have now a more or less, so this is north-south, and that's east-west. So in the same direction as the torus and the disk that was observed before, we find a more or less dusty torus with about 150 to 90 milliarc seconds, and the star is here right in the middle, about 20 milliarc seconds. We can help resolve that one. We also have old observations with another aperture masking experiment with Keck. And at 467 micron, we see a completely different structure, but this was observed at least 6 years before our observations with Lykou. And the shape is completely different, and of course the core is unresolved, is less than 50 milliarc seconds. Last year we observed Lykou again, and this time at 2.30 micron we see a more or less, well, not exactly a round shape anymore. So the star is again unresolved at about 30 milliarc seconds, but the remaining envelope is definitely not spherical in this case. Now for the next target, it's a no oxygen-rich star. So you've heard about this earlier this week, it's L2PAP. And a few details again, it's an oxygen-rich star, it has one of the slowest outflows. Typical outflow for HB stars is 5 to 10 kilometers per second, this one is about 2.5. It experienced a dimming event in 1994. So since then it hasn't recovered, so it dropped down from about the magnitude 5 down to almost 7.5. Hasn't recovered ever since. And there's been some previous observations with Keck in the mid-infrared, where they think that they have found an asymmetric envelope, which is about 2 arc seconds across. So if you want to look closer to the star, you go, these are observations with MAPIT. It's another aperture masking experiment that happened in 2004, if I remember correctly. But it was one-dimensional observations. So in this case, the mask was not spherical, but the one I showed before was just one line of holes. And to model their results, they required again two components. So we have one for the star is about 25 milliarc seconds, and one for a second star envelope of about 80 milliarc seconds. Alright, so we went and observed the star with aperture masking. But the first results that was done about a year ago was with polarimetry. So you use aperture masking, you just put a Wollaston prism on the way and you observe the polarimetric visibilities in this case. So what I show you here is an asymmetric signature. So this is a ratio of visibilities between two different polarization states. If the star was symmetric, it will be all equal to 1. If the star was spherically symmetric, you would see that this pattern was more or less a sinusoid. It would follow, it would be centered at 1. But in this case, it's completely different. So when you go and look at this, so we have this, I just showed you a picture of the envelope before. When you look at this at 2.3 micron, again with polarimetry, you see something completely different. So this is exactly in scale, so whatever was in here, we won't detect it with Keck. Now we detect it in Stokes-Q polarization. And in Stokes-Q, it's also the same image. This is about 200 by 200 meter seconds. So you see something roundish in the core, that's where the star is, and some kind of clumpy structure on the sides. And that's just polarimetric data. And if you go to actual imaging, you see something completely different. So what you have here, the top line is observations at 2.30 micron, and the bottom line is 374. Now the difference between the columns is this is image reconstruction with ESMN, this is image reconstruction with Mason and Myra. It's 3 different types of software to use it to independently reconstruct the images that have been recorded. I have here the resolution elements of the telescopes at both wavelengths. And you see that at 2.30 you have a star and more or less the clumpy structure, but I would like you to trust whatever is from cyan to green to red. You see a clumpy structure, the star is about 20 to 30 milliarc seconds, so it is unresolved. That at the distance of that is about 2 AU diameter. And again, at 2 AU from the star, you see the clumpy structures. It's the same as we observed before. And all 3 image reconstructions are exactly the same. But if you go at 374 micron, you see more or less an elliptical structure. Now we believe that at 2.30 we might have some combination with CO, carbon monoxide. It's the first overtone, so we might be detecting the actual gas from these specific images. We actually have very small waveband in the filters, which was actually good. And we tried now to independently confirm this by applying a geometrical model to this. And the model agrees very well, down to 5% of the images. So we have an elliptical torus, and which is the orange. You can't see it very well here, but it's over there as well. And a white star. So you need both to create the actual data. Now this is some work in progress. There is this big new technique where you can actually subtract the star from the image, and you can see the stellar environment without having contamination. So if we do that, we see that there is a clump here, it's the same one as that over there, and there's more clump on the side, so the star is missing in this case. But this is still work in progress, so take it with a bit of salt in this one. Now what did we learn so far? So we see that asymmetries can be detected even back in the image-to-be phase. The original is from the post-to-be phase, let's say. And the stars, although they might be roundish, they're really not. And there's been some work in progress so far in plenty of carbon and oxygen stars. And these asymmetries tend to form in the shapes of tori or spirals, as in other cases. As compared to what we see in post-AGD and planetary nebulae, where in some cases there are thin disks like the one we had for Mansell 3929, much larger in scale, of course, but much thinner than what we see here compared to the size of the star. And I'd like you to check also the poster B24 and M29, it's an extension of the disk that we found before. And even though the AGDs appear round, there was a mineral paper from Bama Binoris with Lykou, where you see a spherical dust shell. At larger scales, as in the Herschel, you see more or less irregular shape anymore. And some questions. So, in the case of Lykou, the star is believed to have a binary. For the case of LTPAP, even from the interferometric data, we don't say that there's a binary inside. First of all, I'm missing a lot of information, and K2 showed his work on LTPAP earlier has more information on this. If you can see the signal flow of the binary in his larger spatial scales, smaller spatial scales. But I don't know if it is too soon to say that if you can detect them in post-AGD phase, as we've seen in the previous talks, is it too early to detect them in the AGD phase? So if you use interferometry, you could detect them. Of course, there has to be some parameters. You have to consider brightness, you have to consider how far close they are from the companion might be from the AGD star or not. But there are some new instruments coming along for interferometry, because we're still talking about small spatial scale. There's AMBER, there's Pioneer, there's the Imager at VLTI, there's Gravity and Matisse, which will be new instruments coming in the next 3 to 4 years. And for the north, there is always Chara. And you can still use aperture masking with Lykou. It's going to be there for the next year or so. And the new instrument for VLT errors is coming hopefully in 2018. So if you still want to work on this, if you want to see if you can actually take pioneers and locate comps, so just come and talk to me. Thank you.
Thank you. Any questions before the discussion? Bruce? Microphone's coming.
Claire, do we know if the nuclear line is scattered from dust or is it intrinsic to the dust?
Can you repeat that? Can you repeat that?
Sure. Ignoring the central star.
Ignoring the central.
Not that close. You asked for it. Ignoring the central star. Is the radiation that you see off the center line scattered or intrinsic emission?
For the polarimetric maps or the actual maps? Because the positions of the clumps I show you in the polarimetric maps do align with the ones that I have in the normal maps at 2.3 micron. If it's polarized or not, well, there's been some ongoing work from Mark in Australia, so he's looking at in a more detailed study of the star, and he sees a polarized signal even at 2.3. My treatment was not so sensitive, let's say, so I see that they do match, but they're the same in every Stokes Q, which is Q plus of 0, 45, 90, and 135 degrees polarization. It all looks the same.
No question at the back.
Could you show me the images of the Hydra again? 3.74 micron. You show two images taken at 2 epochs. Right, yeah. So the upper panels, the difference, they look very different. So then the difference is due to the time variation?
That could be the case. But this is a much larger scale than this one, so this is about 0. I mean, it looks to be east-west, but it's 0.3 arc seconds.
Yeah.
Much smaller than that.
So, but you don't see the, say, the background or something on the right image is extended angle component doesn't appear.
No.
Because of the sensitivity?
Sensitivity and also my field of view was about 400 milliarc seconds, and I still don't see nothing around it.
Okay.
Any more questions? If not, then the next item on the agenda is the discussion. So if the speakers of this section would make their way to the front to be grilled by the